Hello, and we're recording. Um, Geometry, how you doing? I didn't post a 10.2 video, right? Well, I've decided to kind of split 10.2 into two parts. So this is our 10.2 video. 10.2 video part 2, if you will, and there was never a part 1. So let's take a look. This is the 10.2 notes. They've been posted. You may or may not have downloaded them and took a look at them. So a lot of this stuff that we're seeing is stuff that we already covered in class with our first Socrative. Okay, so some simple probability questions with playing cards. Let's just do one, maybe two real quick. What's the probability of a 10? We know that there are 4 10s. 4 out of 52 immediately reduces to 1/13th, something like that. Or here's one that says a red face card. So we only want these kings, these queens, and these jacks. There are 1, 2, 3, 4, 5, 6 of them out of 52. Those are both divisible by 2, and you end up with 3 out of 26, like so. We answered those questions. Those are pretty straightforward. Then we have these questions where it says a club and a 6, or a black card and a heart. When it says the word and, you could rephrase that as, what is the probability of getting a 6 of clubs? Right? What is the probability if something is a club and a 6 at the same time, the probability, that's essentially a 6 of clubs. So what's the probability of a 6 of clubs? 1 out of 52. Okay, so I don't really like the way these questions are phrased, which is why honestly I'm not even going to bother with that one. When it comes to the word and, right, when we say and, we mean those two things simultaneously. What's the probability of being red and a face card? What's the probability of being a 7 and red? In class, during the Socrative, I said, what's the probability of a red 7? Isn't that kind of the same thing as saying, what's the probability of a red and 7? Right? You see what I'm saying? So don't overthink that. Don't overthink that at all. Please, please, please. Then we have these OR questions. Let me spend a moment on OR questions because they're quite important. When it comes to OR questions, you can add together the individual probabilities, but then you have to subtract where they overlap. Okay? So what's the probability of an ace? 4 out of 52, because there are 4 aces. What's the probability of a red card? 26 out of 52, because half the deck is red. But the thing is, when we counted these 4 aces, we need to realize that 2 of them are red. So there's an overlap, right? We said, hey, here's the red cards, and we said, hey, here's the aces. They're overlapping. We don't want to count that twice. So those 2 red aces are being counted twice. Once in here and once in here. So we only want to count them once. So let's subtract 2 out of 52, because that's the overlap. Excuse me. That's the overlap, and we end up with an answer of 28 out of 52, which reduces to 7/13. You see that? Let's do it again. How about the probability of a heart or a face card? So how many hearts are there? 13 out of 52. How many face cards are there? 12 out of 52. But the thing is, when we counted the 13 hearts, there were face cards. There are face cards inside of these 13. So we're counting the face cards twice. Once in here and once in here. How many are we double counting? 3, because there are 3 face cards in the hearts. So we counted the jack, queen, and king of hearts right here, and then we counted them again. We don't want to count them again. So subtract 3 out of 52, and you end up with 22 out of 52, which simplifies to 11/26. There are moments where there is no overlap. For example, this question. There's no overlap between jacks and fives, right? What's the probability of getting a jack or a five? 4 jacks, 4 fives, 8 out of 52, which gives you a they're both divisible by 4, so you get 2/13. There's no overlap between jacks and fives. You can't have a jack. You can't have a jack that is also a 5. They're completely separate. Okay? Another thing that we did in class with the Socrative was, I know this is an extended review, but the thing is I never made a video, so this is a very quick synopsis, was given. Given. This right here means given. So what is the probability of A given B? I don't want you to think about this formula. Don't think of it like that. It's not wrong. The formula is not wrong, but I'd rather you think of it this way. What is event A? A is a jack. What is event B? That is a heart. So if I give you hearts, what is the probability of a jack? Well, if I give you hearts, there are only 13 hearts. I'm not giving you the entire deck. I'm giving you hearts, and one of those hearts is a jack. Final answer. Okay? If I give you a red card, I'm giving you 26 cards, because that's event C, and A is a jack. So how many of those red cards are jacks? 2 of those red cards are jacks, the jack of diamonds and the jack of hearts, which reduces to 1/13. You see how the given is having a dramatic effect on our denominator, because I'm no longer giving you 52 cards, I'm giving you 13 for hearts, 26 for red, maybe only 12 if you're given a face card. Anything could happen there. You're no longer given the total 52. Now, this is the main new thing that I'm probably an additional 5 minutes, and the video will be about 13 minutes. So here we go. Let me do one, I'll have you do one, and then we'll see where the time's at. So what we're doing here is we have multiple events in a row. We want to know what is the probability of getting a 10, and then you go to pick another card and it's a 5. What is the probability of that happening? Because that's way more unlikely for 2 events to occur, right? It's one thing to say, oh, it's going to be a 5 and then, hey, we got lucky. But what about a 5 and then a 10? Or, sorry, a 10 and then a 5, right? 2 events in a row. The odds aren't really in our favor at that point, right? So what is the probability of this occurring? How do we do this? Well, when you have multiple events in a row, you multiply the probabilities. You multiply. And I'll show you what I mean. Let's read the entire question and then we'll do it. Find the probability of the event if the cards are replaced, not replaced. So I'll tell you what we mean by that. I have 52 cards in the deck, yeah? How many of them are 10s? 4. Okay. And then we multiply that by the probability of the next event. If I pick out a 10 and then I put it back in the deck, in other words, I replace it, I replace the 10. I put it back where it came from, there are still 52 cards in the deck, and now there are still 4 5s. So that's my probability. Now each of these reduced to 1/13. So the answer here would be 1 out of 169. There's a 1 in 13th chance, which is not too bad, of getting a 10. But there's a 1 in 169 chance if you want to do 10 followed by a 5. That's significantly more unlikely. Now, how do things change if there's no replacement? Take a look. The first time around, when we grab a 10, there are 52 cards in the deck, 4 of which are 10s. The second time around, if we didn't replace the 10, if I don't put it back in the deck, how many cards are left in the deck? 51 now. But there are still 4 5s. Our final answer comes out to be 1 over 13 times 4 over 51. 4 over, what's 13 times 51? 13 times 51 is 663. Okay? You see how that sort of changed the game? Now, which is more likely? 1 out of 169 or 4 out of 663? What do you think? What do you actually? Let's just have that as a question. What do you think? Right? When I punch these into a calculator, which is more likely, this or this? Like, which one of these is actually the bigger number? Because fractions can be a little weird. Which is more likely, 1 or 2? Some questions pop up on screen. So I'll pull it up on a calculator here. 4 out of 663 multiplied by 100. There's a 0.6% chance of that happening. Very unlikely. 0.603. That's very unlikely. 1 out of 169? Would you look at that? That's a 0.59 chance. It's ever so less likely. Why? Because when we put it back in the deck, that 10 entered the deck again, right? So there's a chance of grabbing that 10. If we remove that 10, we are removing an option, and therefore the 5 is just a little bit more likely. Just a little bit. By removing that card, the chance of getting the 5 is just a tiny bit more likely. All right. So let's have you do 2 problems here. Part 1 and part 2. So we're doing a king followed by another king. The first question, you put it back in the deck. The second question, you don't put it back in the deck. So think about that. Remember, I multiply the probabilities. That's what you do. You multiply. Event 1, event 2, multiply. So think that through. Some questions pop up on screen, or answers pop up on screen now. So you answered. What's the probability of getting a king? 1 out of 13. I'm gonna jump straight to the point. 4 out of 52, which is 1/13. And if I put that card back in the deck, there are still 52 cards in the deck, and it's another 1 in 13 chance. Oh, it's the exact same as this one. Yeah, it is. It is, right? When everything goes back to normal, it's just going to repeat itself. But now things heat up a little bit here. Let's write this all the way out. 4 out of the 52 cards are king. So that is the probability for that event. But when I remove that king, how many cards are in the deck? 51. And if I want another king, how many kings are in the deck? 3 out of 51. This second half is a little different. Okay, just a little bit. And we end up here with, let's reduce this to 1/13. So we end up with 1 times 3, which is 3. And 13 times 51, which we already did over here, is 663. Now guess what? This reduces a little bit further as well. 663 is divisible by 3, and we end up with 663 divided by 221. So now the first one is more likely, because when you remove a king, that's just no bueno. That is just no bueno when you remove one of the options, right? Now there's only 3. So this probability is way more unlikely, right? Which is why it's, if you've ever played, blackjack, just like with friends, like playing 21 and you're not really gambling, right? But you just, hey, let's play 21. the chances of being dealt two of the same card are very unlikely. And when you play blackjack at a casino, they allow you to split your cards when that happens. When you get two of the same card, you're allowed to split. I forget what it's technically called, but you're able to do two hands simultaneously. I don't know. Look it up. Your parents can probably have gambled. Okay, so let me quickly do one more. What's the probability of getting a 2 followed by a queen followed by another 2? Well, when you replace the card, everything just keeps going back to normal. And this time around, we have 3 events. So 1/13 times 1/13 times 1/13. What is that? 13 times 13 times 13. 1 out of 2,197. Great. But the second you don't put a card back, we had 4 out of 52. When we took a 2, there's only 51 cards left, but the 4 queens are still there. But earlier we took a 2. So if we're going to pick another 2, there's only 3 options left, and we took that queen out, so now we drop down to 50. Now we dropped down to 50. So how does this reduce? This reduces to 1/13. 51 is divisible by 3, by the way. 51 divided by 3. So this would simplify to a 17, and this would cancel out. And then 4 and 50 are both divisible by 2. So this would go to 2, and this would go to 25. So 1 times 2 times 1 is 2. And 13 times 17 times 25 is 5,525. If I lost you, rewind 20 seconds and watch me cross stuff out again, okay? If I lost you, go back 20 seconds and watch me cross stuff out. And with that, that is our part 2. Honestly, this is the part 2, right? These sequential events, and that's going to be the focus. That's going to be the focus. Oh, geez, that sun, what's happening? That's going to be the focus of our Socrative next class and the focus of the assignment. So with that, I appreciate your time. Thank you for watching, and I'll catch you on the flip side. Oh no, where's my button to stop recording? Okay, bye.